In Section 3B, Putting Numbers in Perspective, we'll study the scientific notation, a way of representing very small numbers and very large numbers. In this video, we'll solve problems 1, 2, 3, and 4 um, in the worksheet. You've probably come across scientific notation before. It's a way of writing very large numbers and very small numbers. So for example, if you see 2.5 times 10 to the 27. So instead of writing it as 25 followed by a whole number of zeros and you have to keep track of how many zeros you're writing, it's just easier to write it as 2.5 times 10 to the 27. Or if you see a number like 1.25 times 10 to the negative 5, it can be written as 0.000 0125. So anytime we're dealing with a bunch of zeros, we need to keep track of them and make sure we're writing the correct number of zeros so we're not writing a number incorrectly. It's just easier to write it in scientific notation. So that way, this tells us how many zeros before um, the 125 that we need to have in the number. So that is scientific notation. When you've seen this, you probably know what we're talking about. But let's just quickly go over what the scientific notation looks like. So it's a number times 10 to the, and then a whole number here. So large numbers can be written as some number times 10 to the positive whole number. Now, there are certain conditions that we have to follow. The first number here would have to be a number between 1 and 10. You cannot include 10, but you can include 1. So any number between 1 and 10 times 10 to the positive whole number for a very large number. Now, suppose we have a small number between 0 and 1. So if we have a small number between 0 and 1, we can write it as some number times 10 to a negative whole number. So a negative number over here, but that's a whole number with a negative sign. Now, the same rules have to be followed in this case. The number that sits here must be a number between 1 and 10. 10 cannot be included, but 1 can be included. So that is how a very small number is written. Now, let's do a few problems on the next page. Now, in the first problem, we are given a bunch of numbers here, and we write each number in the scientific notation. So let's look at this number, a very large number. So we know that the exponent in the scientific notation would have to be positive, just the exponent. Now, we need to make sure that we write the number as something times 10 to a positive whole number. Now, this number here must be a number between 1 and 10. So let's start off with the process. It's a large number. There is no decimal point, so we place the decimal point at the end. So what we do now is move the decimal point one place at a time, and we stop only when we get a number between 1 and 10. So we start with the decimal point here and move places 1, 2, so 1, 2, 3, 4, 5, 6. So I stop here because if I place the decimal point exactly after 1, then I have 1.233476. So what I have here, 1.233476 times. Now I need to make sure that the value of the number remains exactly the same. We're only going to write it in a different form, but we cannot change the value. So how do I make sure that the value of the number is the same? I multiply with 10 to the 6th power. So when I multiply with 10 to the 6th power, the decimal point that I moved to the left by 6 places is going to move back to the right by 6 places. And this makes sure that the number is unchanged. So 1233476 can be written as 1.233476 times 10 to the 6th power. Now let's look at the next number. 43 followed by 9 zeros. So we don't see a decimal point anywhere. So we can assume that the decimal point is at the end. Now we keep moving the decimal point to the left until we reach a number that is between 0 and 10. So if I stop and place the decimal point right after 4, I get 4.3, and that's a number between 0 and 10. So that works for us, between 1 and 10, I'm sorry, and that works for us. So we write our um, decimal, we write our number in the scientific notation as 4.3, but we can't stop there. We need to make sure that what we just did by moving the decimal point to the left by 10 places is undone by moving the decimal point to the right by 10 places, and that's exactly what this 10 to the 10 does. So 4.3 times 10 to the 10th power is the same as 43 followed by 9 zeros. So that's 43 billion. So 43 billion is the same as 4.3 times 10 to the 10th power. It is so much easier and convenient to write a number in this form rather than in this form, where we have to keep counting the number of zeros, making sure we've written it correctly. Now the next problem, it's a negative number, negative 234.480. So the number is negative, so we stick a negative sign in front of it. We need to write it in scientific notation. So again, the decimal point has to be shifted enough places so we get a number between 1 and 10. So if we stop here, we get 2.34480. So that's how we get this number. But then we move the decimal point back by 2 places by multiplying the number by 10 squared. So if we move to the left by 2 places and then to the right by 2 places, basically the decimal point remains the same, which means that the number is unchanged. So the last number in problem 1 is 0.00000000254. So it's a very, very small number between 0 and 1. It's a positive number. Now we need to write this in scientific notation, which means now what we need to do is we move the decimal point to the right and we stop only when we get a number between 1 and 10. So we take this decimal point, move it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 places to the right, which makes it 2.54 times 10 to the negative 10. So why is it times 10 to the negative 10? It's because we've moved the decimal point to the right, which is the same as multiplying with the 10 to the 10th power. To, to compensate for that, what we need to do is to shift the decimal point back by 10 places, and that is the same as multiplying with 10 to the negative 10. So moving the decimal point to the right and then moving it to the back again to the left, the exact number of places keeps the number unchanged. So the scientific notation for that really small number is 2.54 times 10 to the negative 10. So small numbers between 0 and 1 have a negative exponent. So a beam of light can travel the length of a football field in about 30 nanoseconds. So nano is a short form for 1 billionth. So 1 nanosecond is 1 billionth of a second. So 1 billionth of a second is 1 over 10 to the ninth power of a second, which is equal to 10 to the negative 9 seconds. So we need to answer the question by changing the units from nanoseconds to seconds. That's all we need to do. So 1 nanosecond is 10 to the ninth, 10 to the negative 9 seconds. So we need to change the units from nanoseconds to seconds. So we consider the two ratios, 1 nanosecond over 10 to the negative 9 seconds, or 10 to the negative 9 seconds over 1 nanosecond. The second one is what works best for us because we want to be able to cancel out nanoseconds and make sure that our final answer is in terms of seconds. So 30 times 10 to the ninth power and seconds, which is the unit that remains. So this is the same as 3 times 10 times 10 to the negative power. Using the rule of exponents, it's the same as 3 times 10 to the negative 9 plus 1. When we multiply two numbers with the same base, all we have to do is add the exponents. So 10 to the 1 times 10 to the negative 9 is equal to 10 to the negative 9 plus 1, which is equal to 10 to the negative 8. So 30 nanoseconds is the same as 3 times 10 to the negative 8 seconds. So we've converted that number into scientific notation. We used the basic idea of exponents to do that. Now, the next topic is order of magnitude. So what is the meaning of order in magnitude? when we talk about the number of times in a week that we eat, so that would be in tens. It could be, um, if suppose we eat 3 times daily in a week, that would be, um, 7 days in a week. 7 times 3 is 21. So basically, 20 meals per week is in tens. What if it was, um, 300 times a week? So your answer is in hundreds. If something is like done 3,000 times a week, then your order of magnitude is in the thousands. So sometimes, just to get an idea of how large a number is, we just say it is in the tens, or it's in the hundreds, or it's in the thousands, or it's in the millions. So that is what order of magnitude means. So question number 4, it says the number of steps you take in an average day, find the order of magnitude. So find the order of magnitude of the number of steps you would take in a month, and find the order of magnitude of the number of steps that you would take in a year. So in a day, let's assume we have a healthy habit of taking 10,000 steps. So we're just making that assumption that the number of steps that you would take in a day is 10,000. 10,000 is 10 to the fourth power. So the number of steps that we take in a day is in the thousands, because it could be 9,000, 7,000, 5,000, and depending on how active you are, it could be 2,000 to 3,000 steps per day. So the order of magnitude is in the thousands. Now, in a month, there are 30 days. So if in a day we take 10,000 steps, in a month it would be 10,000 times 30 steps. So that is 300,000 steps. Now, the order of magnitude here is in hundreds of thousands. So 100,000 is the order of magnitude. In a year, there are 12 months. So if in a month we take 300,000 steps, that's 3 times 10 to the fifth power steps. Since there are 12 months in a year, and this is the monthly number of steps, we need to multiply, not with 365, since there are 12 months in a year, it would have to be multiplied by 12, and that would change all the answers. So this would be 12 times 3, 36, followed by 1, 2, 3, 4, 5. So that should be our answer. That's 3,600,000 steps. So the order of magnitude would then be in the millions. So notice the error here. If this is the monthly number of steps, so in a month, if we take 300,000 steps, and if there are 12 months in the year, I should have multiplied it with 12, not with 365. And that would give us the final answer. Now, another way of calculating the number of steps in a year is by taking 10 to the fourth power, which is the number of steps in one day. And now that number, if it's multiplied with 365, that would give us approximately the same answer as this. That is the total number of steps taken in a year. So notice the error here.